We now start the discussion on the module number 2 of chapter 3. In the last module, we have already defined the notion of measurable functions, and we have seen certain properties of the measurable functions, and in this module we will just continue in that way. We will discuss more properties of measurable functions, and we first go to the first slide now. We start with a very basic notion in measure theory, which is used very often in many places in measure theory. A property P is said to be satisfied almost everywhere in R if there is a measurable set E of Lebesgue measure 0 such that the property P holds everywhere in E complement. Let us see two examples. Consider the function chi q on R, that is the function which takes the value 1 at all rational numbers and takes the value 0 at all irrational numbers. Consider the function f defined by f(x) equal to p for every rational number x, where the rational number x is of the form p by q, where obviously GCD of p and q is 1, and it takes the value 0 otherwise, that is it takes the value 0 at all irrational numbers. Now, if we compare the functions chi q and f, see that at all irrational numbers the values of both the functions are 0. The value only differs on the rational numbers, and we already know that the set of rational numbers is a countable set and is a set of Lebesgue measure 0. So, we can conclude that chi q and f are equal almost everywhere. Another example is that if we consider a monotone function, we know that a monotone function can have at most countable number of discontinuities. Again, since a countable set has Lebesgue measure 0, so a monotone function can have discontinuities at most inside a set of measure 0, and consequently we can say that every monotone function is continuous everywhere almost. Now, we start with another result, lemma 1. Let f and g be two functions defined on a measurable set D. If f is measurable and f is equal to g almost everywhere, then we are going to show that g is also measurable. For this, we start with a real number alpha belonging to R. Let us write the set A as collection of all x belonging to D, where f(x) is greater than alpha, and the set B as collection of all x belonging to D, where gx is greater than alpha. See that since f is measurable, we already know that the set A is measurable. We have to show that the set B is measurable in order to show that G is measurable. Now, since by our assumption f is equal to G almost everywhere, so the points where f is not equal to G is a set of Lebesgue measure 0, and consequently both the sets A minus B and B minus A, where obviously f x is not equal to g x, have Lebesgue measure 0. Now, we can write the set B as B minus A union B intersection A, and which is equal to B minus A union A minus B. Now, clearly both the sets on the right hand side are measurable, and so their union, the set B, is also measurable, and this shows that the function G is measurable. Next, we prove another result. We can already prove that a continuous function is measurable. Why? Because by definition, what is a continuous function? A function f is continuous if the inverse image of an open set is an open set. So, if f d to r is a continuous function, then the collection of all x belonging to D, where f x is less than alpha, this is nothing but the set f inverse open interval minus infinity alpha open. Now, since open interval minus infinity alpha open is an open set, so its inverse image is also an open set, and we have already seen that open sets are also measurable. So, continuous functions are always measurable, but we are going to extend that result by showing that if a function f defined on a measurable set D of R is continuous almost everywhere, then also f is measurable. We start our proof by our assumption f is continuous almost everywhere, which means that if we consider the set E of the points of discontinuities of f, then the set E has Lebesgue measure 0. So, for any given alpha belonging to R, if we consider the set x belonging to D, where f x is greater than alpha, we can divide the set D into two parts, E and D minus E. So, this particular set x belonging to D, where f x is greater than alpha, this can be written as union of x belonging to E, where f x is greater than alpha, and x belonging to D minus E, where f x is greater than alpha. Now, look at the first set on the right hand side. This is a subset of E, and E is a set of Lebesgue measure 0, and so this set also has Lebesgue measure 0, so is measurable. Hence, to show the measurability of f, we only have to show that the second set is also measurable. Let us write the set x belonging to D minus E, where f x is greater than alpha, as C. We first note that since all the points of discontinuities of f are in E, so f is continuous at every point of the set C. And consequently, for any x belonging to C, using the continuity of f at x, we can find a delta x greater than 0 such that f y is greater than alpha whenever y belongs to collection of all u belongs to D, where mod u minus x is less than delta x. Now, let us take the union of these sets U, where mod u minus x is less than delta x and x runs over C as the set U, that is U is the union x belonging to C, collection of all u where mod u minus x is less than delta x. Now, each set on the right hand side is an open interval. So, their union is an open set. So, U is obviously an open set and consequently, U is a measurable set, and subsequently see that C is actually equal to U intersection D minus E, and so the set C is also measurable, and this proves our assertion. We will now again go back to the definition of a measurable function. Recall that the function f d2r is measurable if and only if one of 4 conditions hold, which are that collection of all x belonging to D, where f x is greater than C, or f x is less than C, or f x is greater or equal to C, or f x is less or equal to C, these sets are measurable, and consequently we have the conclusion that f inverse singleton set C, that is the collection of all x belonging to D where f x is equal to C, this set is also Lebesgue measurable for every C belonging to R. Now, the question is the converse true? That is, if I have a function f from R to R such that f inverse of singleton set C is Lebesgue measurable for every real number C, is it true that f is also Lebesgue measurable? The answer is no. Consider a non-measurable set E of open interval 0 1. Recall that we had constructed such a set in chapter 2. Define the function f in this way: f x equal to e to the power x 2 chi e minus 1 on R. Clearly, the function takes positive values at all points of E and f(x) is less or equal to 0 on R minus E. F is also injective and consequently F inverse singleton set C, that is collection of all x belong to R where f(x) is equal to C, is either empty or a singleton set for each C belonging to R, and in each case this set is measurable. But observe that if we take f inverse of open interval 0 infinity, then this is equal to the set E, which is already a non-measurable set, and this shows that f is not a Lebesgue measurable function. So, the condition that f inverse singleton set C is measurable for every C belonging to R is a necessary condition for measurability, but it is not sufficient. Next, we are going to prove a very important result. If f closed interval a b to R is a measurable function, then we are going to show that there is a unique real number R satisfying this property, that measure of collection of all x belong to closed interval a b where f(x) is greater or equal to R, this is greater or equal to b minus a by 2, while the measure of the collection of all x belonging to closed interval a b where f(x) is greater or equal to s, where s is greater than R, this measure is less than b minus a by 2. For this, we consider a function capital F from R to R defined by f of C as the measure of the collection of all x belonging to closed interval a b where f(x) is greater than C for all C belonging to R. Observe that since f is measurable, so this particular set is measurable and so its mu value exists. Obviously, the function capital F is a non-increasing function on R, and if we take limit C tends to minus infinity, we get capital F of C is equal to b minus a, and limit C tends to infinity, capital F of C is equal to 0. Now, let us write the set C belonging to R where capital F of C is greater or equal to b minus a by 2 as the set capital A. Obviously, capital A should be a non-void set which is bounded above, and consequently supremum of A, which we can say R, exists, because we know that by the completeness axiom of real numbers, any non-void set of real numbers which is bounded above must have a supremum. Now, clearly for all s greater than R, measure of collection of all x belonging to closed interval a b where f x is greater or equal to s, this is less than b minus a by 2. And finally, choosing an increasing sequence R n which is converging to R, we have this observation that mu of collection of all x belong to closed interval a b where f x is greater or equal to R, this is equal to mu of union n equal to 1 to infinity collection of all x belong to closed interval a b where f x is greater or equal to R n. See that R n is an increasing sequence converging to R. So, R should be the supremum of those R n, and so f x greater or equal to R means f x should be greater or equal to R n for at least some n. Again, this is equal to limit n tends to infinity mu of x belonging to closed interval a b f x greater or equal to R n. Here we use the fact that Lebesgue measure is continuous from below, and this is greater or equal to the number b minus a by 2. And finally, we are not checking it in this presentation. It is quite easy to check that the number r which we have defined is a unique real number. Let us summarize what we did in this module. The main thing what we did in this module is that we have defined the almost everywhere concept. A property P is said to hold almost everywhere if there is a set A of Lebesgue measure 0 such that the property P holds at every point outside the set A. And we are going to use this concept more and more later in all the chapters of measure theory. We have also seen that if a function f is measurable and if we take a function g which is equal to the function f almost everywhere, then the resulting function g is also measurable. And we have also observed some special properties of measurable functions, and one of the main properties which we have proved is that if a function f is continuous almost everywhere, then the function f should be measurable. And with the help of this observation, we can get another observation that every monotone function is also measurable, because all the monotone functions have countable number of discontinuities at most. So, monotone functions are continuous almost everywhere. With this, we finish this module.